Alright goofs, here's a real quick video taking you through how to solve this math. We'll do more practice later. This is just an intro, just a touch. So it says calculate the numerical population change delta N for Willow Creek in 2024. So your population change formula is births plus immigration in parentheses minus deaths plus emigration in parentheses equals delta N. So my births, 1,200, plus my immigrations, from right there, are 150, minus deaths, which were 400, comes from right there, plus emigrations, which were 50, come from right there. We do the math, we get 1,350 minus 450 equals 900. So the question was asking, calculate the numerical population change. So my delta N is 900 people. Now, if the question was asking what is the new population, which is a thing that happens sometimes, then you would take the new population and add that to your starting population, which would give you 45,900. You just have to pay attention to the question that's being asked. Now, in this case, it wants to know what is the change. So really, that was terrible. Our correct answer would be 900 people. If we got a negative number there, then that's fine. That just means our population shrank. But we had more births than deaths and more immigrations than emigrations. So our population should have gone up, which our math supports. Now, the next part, calculate the population growth rate as a percentage. So for that, we need our accrued birth rates and our accrued immigration rates and our accrued death rates and our accrued emigration rates. So what you do is you take your births, divide by your starting population, and then you multiply by 1,000. So we get 1,200 divided by 45,000 times 100 times 1,000. My mistake. Now, pro tip, the zeros cancel out. So really you end up with 1,200 divided by 45. That ends up giving us 26.67 CBR. Now, instead of walking you through the rest, you do the same thing for deaths, immigrations, and emigrations. It's you take each of those values, divide by your starting population and times 1,000, or take that number you get and divide by 45. But my accrued death rate ends up equaling 8.89 is my CDR. My CIR is 3.33 IR, and then my accrued death rate, accrued emigration rate, my mistake, is 1.11 CER. So then you end up with accrued birth rate plus accrued immigration. You just come back to this formula, except now you're going to use accrued instead. So CBR plus CIR minus CDR plus CER, and this time you add the extra step of then divide by 10. And you end up with your growth rate equals 2%. So the question was asking us, boom. Now, there is a special way you have to enter this into Bluebook, but we'll practice that again later. We're just rough-handing it right now on paper. So then C, if the growth rate calculated in B remains constant, predict the population size at the beginning of 2025. So we were starting off at the beginning of 2024, and it wants to know what it will be at the beginning of 2025. So 1 year's worth of growth, and we know how much it's going to change. We actually calculated 2 different ways it'll change. Now, you only need one of these, but we'll do both. Now, the super easy one, we know that we're going to add 900 people in 1 year. So it would be our starting population, 45,000, plus 900. And that gives me 45,900 people. Always put units. Or we can predict what a 2% growth is. So you take your starting population and then multiply by a 2% increase, which would be 102% of your starting population. Either way, you end up with that's a terrible 45,900 people. Either way is acceptable. College Board will always accept the math as long as it is equivalent. Okay, so we have a growth rate of 2.1%. It says calculate the approximate doubling time for the nation's population in years. Now, whenever you see doubling time, your brain should immediately think rule of 70, which is dt, doubling time, equals 70 divided by your percent growth rate. So your R. Now, my R was 2.1%, so doubling time equals 70 divided by 2.1, and that equals 33.33 years. So about every 33 years is when my population's going to double. Pretty reasonable. You know, if you use your common sense, let's round that down to 2%. If it was doubling if it was growing at 2%, it would double every 35 years. 2.1 is a little bit higher than 35, so 33.3 is a very reasonable answer. Now, when you guys were solving this one, a lot of you made this more complicated than it needed to be. Your current population is 100 million, and the growth rate remains constant. Calculate the approximate population size when the doubling time is reached. Keyword there, doubling time. If it doubled, the population has doubled. So you take 100 million, and you just multiply by 2 times 2. So your answer, 200 million, or you can do 200 million. You can write out the word million, or if you were super cool, you could do scientific notation, which would be 200 times 10 to the 6th. As long as it's mathematically equivalent, it's fine. Now, second page. It says calculate the crude birth rate per 1,000 people. You're going to take total births, divide by total population. I'm going to shorten that to total pop. Total pop times 1,000. And you end up with 8 billion. Nope, my mistake. That's the total population. Your total births for 110 million. 110 times 10 to the 6th divided by your total population, which is 8.1 times 10 to the 9th. Your scientific notation's super handy to help you learn. Oops, my mistake. Times 10, 1,000 gives you a crude birth rate of 13.58 is my CBR. Calculate the crude death rate per 1,000 people. Same thing, but now we do total deaths. Total deaths divided by total pop. Oops. Times 1,000. And that gives me a crude death rate of 6.79. There we go. Perfect. Now, on the previous page, we took into account immigration and emigration. We don't do immigration and emigration because this is for the world. No one is entering or leaving the earth. So, immigration and emigration cancel each other out. Now, for my growth rate, it's crude birth rate minus crude death rate, because again, we're ignoring immigration, emigration, divided by 10. I get 13.58 minus 6.79 divided by 10. You get 6.79 divided by 10. Oops. Equals 0.68%. Now, we could do a follow-up question. What would be the doubling time? And the doubling time would be 70 divided by 0.68%. I don't know off the top of my head what that will be, but that would be your doubling time. Now, this question is not asking for it, but if it was. Now, population density. It's your population divided by your area. Since population density is number of individuals per unit of area, per means divided by, So population divided by area. I get 300 individual orchids per 1,200 square meters. 1,200 meters squared, and I end up with 0.25 orchids, terrible C, per square meter. If you wanted, could you write out the words per square meter? Yeah, it's mathematically equivalent, it's fine. Now in this case, the preserve is expanded to 1,800 meters, and the orchid population grows to 400. It's still population divided by area, so this time it would be 400 divided by 1,800, and then I get 0.22 orchids per square meter. Too easy, too easy. Okay, then the last one, it says challenge question, but really it's only challenge because you're multiplying by really large scientific notation. But for part A, would be 5 times 10 to the 6th times 1.5 times 10 to the 3rd. And you end up with 7.5 times 10 to the 9 kilowatt hours. Since a kilowatt hour is just kilowatts times hours, that's what this unit is. There's no per, so it's not per hour, it's kilowatt hours. It's a weird unit of energy consumption that people use. If you wanted, like, the scientific notation is much, much easier. If you didn't use the scientific notation, it would be this: 5 million times 1,500 equals 750,000,000,000 kilowatt hours. All those zeros, that's personally why I prefer to work with scientific notation, because if you miss a zero, your answer is now wrong, and we don't love that. So scientific notation is the way to go. If you're absolutely super uncomfortable and you can't do it, then okay, I guess don't, but I like it. Now, it says it's 80% efficient, which means in order to meet that 7.5 billion kilowatt hours, I need to produce 20% more than that. So what that tells us is that 80% of my total energy is going to equal 7.5 billion. And then there's a one-step algebra problem. You solve from there, you cross-multiply, all that lovely stuff, and we figure out that we need 9.375 times 10 to the 9 kilowatt hours. Lovely.